Right, in today's lesson on contactors, we're going to look at replacement and selection of contactors on site or for new installations. Firstly, replacement of contactors. If you're going to replace a contactor, you can either try and replace it with the same brand and model, which is sometimes difficult. Depending on the supplier, they all sell different brands, depending on what your boss wants to stock in your vans. They're going to be different brands. So if you can get the same contactor, all you're going to do is replace it with the same model number and ensure that the coil inside is the same voltage of the circuit you're putting on. Otherwise, if you put on the wrong circuit, it's probably going to go poof and then you're up for another coil. Plus you look like an idiot. So they're the two basic things. The other thing is make sure the contactor is going to fit on the DIN rail in the switchboard you're going to put it into. Some contactors are slim, some are narrow, some are fat, whatever. They don't fit, so it's just common sense stuff as far as replacement goes. If you can't get the same contactor, the same brand, then a couple of things you need to be aware of is, firstly, you're buying another brand, ensure the coil voltage is the same, so it'll be written somewhere on the contactor. Ensure that you've got the right amount of terminals for your application. In this case, we've got 4 poles. So this might be for a 3-phase motor and an auxiliary contact switching something on or off at the same time as the contactor is energised or de-energised. So you make sure you've got the right amount of poles. The third thing to look for is to make sure that the frequency is the same frequency. So this is 50 Hertz. In Australia, it's 99% of the time you won't have to worry about that. It will be 50 Hertz. It just depends on some specific applications, marine applications and things like that, where the Hertz might vary. Especially on American equipment, it'll vary, and so will the voltage. And the main one you've got to look for is the current carrying capacity of the contacts. Now, contactors switch two types of loads in our industry: inductive loads and resistive loads. Resistive loads are purely resistive, things like electric heaters, and if they're rated at 10 amp current draw, when you switch the thing on, the maximum current it's going to draw is 10 amps. So that's with a resistive load. Whatever the rated amperages of the resistive load, that's the maximum amps it's going to pull. Inductive load is different. That's for any magnetic type device, electric motors, anything that works on magnetic principles. So in our case it's mainly motors. As you know, when a motor starts up, it has what we call lock rotor current, which can represent 7 times its normal running current. So a 10 amp motor, for example, might draw 60 to 70 amps for a split second on startup. This will affect the switching of the poles. The contacts will actually arc if the contactor is not designed to take that high current for that split second. By looking on the side of the contactor, it will have ratings on it called AC1, AC2 or AC3. AC1 and 2 are used for inductive resistive loads like electric heaters. So if it's a 10 amp heater and you look on the side of it and it says it can handle 10 amps resistive, well, you're right, you can put that on. Normally you get a contactor that's a little bit bigger, so it increases the lifespan of the actual contactor. So I'd probably go and put a 15 amp contactor on a 10 amp resistive load. But as far as AC3 goes, you need to ensure that the contacts will handle the motor that you're putting on it. Now, the AC3 rating on these contactors is normally written on the side in kilowatts. So if it's a 5 kilowatt motor, you want to make sure that the contactor has an AC3 rating of a minimum of 5 kilowatts. And as I said, I normally go bigger, say to 7.5, 10 kilowatt contactor, because the difference in price is negligible. But it'll increase the lifespan of the contacts if they're not switching a heavy load all the time. Most of these contactors are DIN rail mounted. That means they'll clip onto a DIN rail in the switchboard. Some have to be screwed into the board. Just be careful when using screws where they're going to end up. So as long as we ensure that the rating for the contactor for current, the coil's correct, the thing will fit in the place that we need to put it into, and it has the right amount of poles on it, you're pretty sweet. An accessory that does come with these contactors is what we call an auxiliary contactor block, which actually clips in, slides in and clips in to the top armature, plastic section of the armature there. So instead of switching 4 poles, I can add another 4 on top. I can switch 8 poles with the same contactor, because as it pulls in, it will pull the connection on the auxiliary block in too, which will shut another 4 poles at the same time, or another 4 circuits. In doing so, we can now have 8 poles on our contactor. Now some of them go a lot bigger, some also have timers that can attach to the top of them and all different types of configurations. But that's the main concern as far as replacing and installing contactors. And that's for today's session. Thank you. Okay, for our lesson today, we're going to be looking at the construction of a contactor. A contactor is an electromechanical device which can switch several circuits at the same time. This contactor here is actually what we refer to as a 4-pole contactor. It's got 1, 2, 3, 4 separate circuits or separate switches operated by the same mechanism. The most common use for this type of contactor is for a 3-phase motor, and the auxiliary contact might be used for something like a crankcase heater that we want to run when the compressor is actually off. In this case here, this particular contactor here, they're all normally open contacts, which means when the contactor is de-energized, that in other words it has no power on it, all 4 circuits are open circuited. Now, to show you the construction of the contactor and what's actually inside it, I've actually pulled the screws out. It had 2 screws, one here and one on the other side, so I just whacked the screws out, and that lets me pull the contactor apart. So now I've pulled the screws out, I pull it apart, and I expose the insides of the contactor. Now, the bottom half of the contactor, which does all the work, comprises of a coil, and this is just a plastic extrusion that's had hundreds of little fine wires wrapped around it, so that when it's energized, a magnetic field's created. When it's installed inside the contactor, I'll put it in the right way, it fits around a metal component in the bottom of the contactor called an armature, which is laminated pieces of steel. So it's about 50 or 60 plates all joined together. The reason it's laminated is to reduce eddy currents and stopping the contactor from overheating. Now, as you know from magnetism in previous courses, when I wrap a wire or a conductor around a metallic object and run a current through the wires, the metal object becomes magnetized, and hence an electromagnet. And in this case the same thing happens. When the coil's energized, it creates a magnetic field which turns our little piece of metal in the armature in the bottom here into an electromagnet. The effect that has is that above it, held up by a spring, is the other half of the armature, so that when the coil turns the bottom half into a magnet, it tries to pull this half of the coil, the armature, straight into it, pulling it in and closing the contacts. There's a fair bit of force there when it does it. Now that keeps it pulled in once that coil's energized. Once the coil is de-energized, so we take the power off, the active and neutral off, the spring will automatically force this back into the open position in a snap action, and that's the force of the spring forcing it back up to open our 4 circuits instantaneously. The reason we want it to open in a snap action is that so it's not slow and we don't get any arcing. If you look down inside, you can see a set of contacts on that side and a set of contacts on that side for that pole and that pole there. The other 2 are hidden behind this metal part, which we're not going to pull apart, otherwise we're going to have to bust the thing. We don't want to break it. The coil in this particular contactor is supplied by, be able to see that. 240 volts with a 50 hertz supply, which is your standard Australian supply. In a lot of applications, air conditioning control circuits use 24 volt coils. Some refrigeration circuits use 415 volt coils. So by pulling the contactor apart and pulling the coil out, I can change it to suit the supply voltage of whatever I'm using it for, and put the new coil back in, whack it on, and off I go. So you can keep a couple of these coil contactors in stock in your van and have several coils in there, so you can use them for several different service applications. The main service issues with these things is either the contactor itself has some sort of mechanical damage and it falls off centre and jams. That will result in the coil burning out. If the magnetic field cannot be made in the armature when it pulls in, the coil will burn out. If the supply voltage is wrong, the coil will burn out. Or if the coil is controlled by a pressure control that has vibrating contacts, which in turn cause this thing to activate and deactivate very quickly, the coil will also burn out. So they're the main reasons for the coil burning out. Apart from that, they're very reliable, these things, especially these days, and they're nice and compact, and they come in varying sizes. So that's it for how a contactor is constructed.